Hello guys, my name is Tanish Parihar. Today, me and my project partner Pranav Kotili Radhakrishna, we will be presenting on a project topic that is using artificial neural networks to do grocery sales forecasting. In our presentation, first we will give a brief introduction about our topic, and then we will talk about the problem that we are trying to solve in this project, uh, and then talk about the data set that we used for this task. After that, we will talk about the different approaches that we use to solve this problem and the results that we got from our experiments. And finally, we will conclude the presentation by talking about the best performing model. What is forecasting? Forecasting is nothing but prediction of what might happen in the future time frame. A forecast could be about the weather, the sales of a product, or could be a forecasting about a natural disaster and so on. So we perform this forecasting by using historical data in which we try to capture trends that might help us in predicting the future. For our project, we will be focusing on grocery sales forecasting. So why is sales forecasting so important? It is because it can play a major role in the success of an organization. By predicting how much to order or produce, they can efficiently manage their budget or the inventory to make huge profits. So, all kinds of organizations, big or small, perform forecasting to efficiently run their organization. For our project, we used a dataset provided by Corporation Favorita, which is a large grocery store chain in Ecuador. The dataset consists of several files containing information about the products, stores, and the changes in sales per product over time. For each product, we have information like the family of the items to which it belongs, whether it was being promoted, whether it is perishable, and so on. Also, for each store, we have the daily total transaction, geographical information, cluster type, etc. We also have been given information about the holidays in Ecuador, since it is known that it can highly affect the sales in the country. Finally, we also have the oil prices for the period of 2012 to 2017, since the Ecuadorian economy is heavily dependent on it. As we can see, we have been given the sales information at the store level, family and individual item level. So this clearly indicates that the data has a hierarchical structure. Due to this, simple forecasting methods will not give us accurate results. So we tried more complex approaches to perform forecasting at different levels of the hierarchy, which we thought can give us better results. Here is a plot of unit sales aggregated by the date. We wanted to show this graph because it clearly shows that there are seasonal trends in our data, which we will try to capture by using artificial neural networks. One more thing to notice is the unusually low sales on some of the dates. By exploring further, we found that the sales were recorded on 1st of January of every year because either the stores were closed or very few people came to shop. Next, we will talk about the different approaches that we use to predict the unit sales, and also we'll show the results that we obtain from our experiments. So first we experimented with using a static supervised learning approach to predict the unit sales of a different family of products at different stores. Due to the high dimensionality of the data set, training the model with all the data will have not been possible. To reduce it, we decided to create two separate embeddings for the stores and the family of the products. For this, first we group the data by the store number and the family of the product. For each group, we added a 7-day lag of unit sales, weekday, month, and other features unique to the group. Using these features, we trained two plain backpropagation models for the two groups with unit sales as the target variable. We experimented with different architectures and optimization methods to choose the best performing model. Then we extracted the first hidden layer of both the models to use it as an embedding. For the final prediction, we combine the two embeddings depending upon the date, store number, and family of the product. We pass this combined with embedding as feature as features to a plain backpropagation model to predict the unit sales. Here are the results that we obtained while training a subset of data to choose the best architecture for training the embedding for the item family. We had around 33 different family of items and other features that we used to train this embedding. As you can see from the graph that the best performing model had 16 nodes in the hidden layer and was trained using Adam optimizer and batch size of 32. Then we use these parameters to train our item family embedding with all the data. So in conclusion, here instead of using one hot encoded features, which will have almost 59 columns, we were able to store all this information into a single embedding of 16 nodes and thereby reducing the size by almost more than 1/4. We performed similar experiment for stores as well. From our experiments, we selected the model with 25 nodes and trained using Adam optimizer and batch size of 16. By training and embedding, we were able to compress the information of 54 stores into a 25 nodes embedding. Finally, we combined both the embeddings to use them as features for our final model. Here is the graph that we plotted for the training process of our final model. We can see that our model is providing reasonable predictions since the validation loss is pretty low. Further, Pranav will talk about other approaches that we used and we will see how the results obtained from this model stands in comparison to other models.
Thank you, Tanishq. Now let's come to the bottom-up approach. So you can see from the diagram on the right that the data can be divided into a hierarchy. At the top level of the hierarchy, we have the grocery store chain. This is the data as it is, meaning that the data is at the item and store level at the top level. In the middle level, we have three geographic regions. So each store falls into one of these three geographic regions. At the bottom level of the hierarchy, we have families of items where each item falls into one of these families. Now, these families are nothing but categories of items such as grocery, deli, and meats. So in this diagram, we have three families. However, in reality, we have about 33 families of items. Now, for the bottom-up approach, we will filter out data based on the region and the family. So what we would do is we would obtain a data set consisting of data from the region coast and the family grocery. We would aggregate this data based on the date and we would run a model for this subset of the data. And then we would repeat this process for every region and every family. In the end, we would run about 99 models. So when a new data point is presented to us, we can look up the model based on the existing region and family, that is the region and family in the new data point. And we can use that model to make the prediction. Now, in order to optimize this, we followed two different approaches to determine what the best model is to be used in the bottom-up approach. We will come to this in the upcoming slides. The first approach we use is univariate aggregation. In this approach, the data is grouped in terms of date, and then the sales value is summed up. And then we create lag variables for the target variable, which in this case is the sales value. And finally, we run models on this data set using grid search for optimization. So we ran plain backpropagation, backpropagation through time, LSTM, GRU, bidirectional LSTM, and bidirectional GRU. and we used grid search to experiment with different numbers of layers and nodes for each of these models. And in the end, I believe we had around 63 different models across all of the different model types. In this slide, we can see a comparison between the best models of each of the different model types. We can see that the best performing models here are the bidirectional LSTM and bidirectional GRU, whose performance is an order of magnitude better than the other four model types. This slide shows a comparison between the different model types in terms of the execution time. So you can see that plain backpropagation has by far the best execution time. And when it comes to the two bidirectional models, bidirectional GRU has a far lower execution time than bidirectional LSTM. Since the mean squared error obtained from the two bidirectional models are almost identical, and bidirectional GRU has a far superior performance in terms of computational effort, we concluded that bidirectional GRU is the best model for this approach. The image in the slide shows the comparison of the predicted values of bidirectional GRU versus the actual values in the test set. The second approach that we used is multivariate aggregation. This approach is similar to the univariate approach, the only difference being that instead of just using the target variable, we are also using the oil price to make the prediction. So in this case, we are creating lag variables for both the oil price and the target variable, and using the resulting data set to train our models. The experimentation in terms of the models is quite similar. We ran grid searches over the same model types and decided on which model is the best model to be used in the bottom-up approach. Coming to the results of multivariate aggregation, this slide shows a diagram which compares the performance of the best model in each of the model types. We can see that once again bidirectional LSTMs and GRUs have the best performance, with bidirectional LSTM being marginally better than GRU. Slide shows a comparison between the best models of each model type in terms of the execution time. We can see that once again plain backpropagation is the best performing model. Between the two bidirectional models, bidirectional LSTM has a better performance. Based on the model comparisons shown in the past two slides, we can conclude that bidirectional LSTM is the best performing model. This slide shows a graph with the actual values versus the values predicted by the multivariate bidirectional LSTM. Comparing the two approaches, we concluded that the best model is the multivariate bidirectional LSTM. So we use that model to run each of the 99 models in our bottom-up approach, and the aggregate MSE of the 99 models is 0.00057,898. After the bottom-up approach, the next approach we tried was the single model approach. So here what we did was we aggregated the data based on the date, region, and the item family. And then we ran models on a subset of this data using grid search for optimization. The experimentation we did here was similar to the experimentation we did for univariate and multivariate, where we ran multiple models and found the mean and standard deviation of each of those models. And we compared the results of each of these models and found the best model. And finally, we ran the final model on the entire data set using the best model architecture obtained from the experimentation. Here we see a comparison between the best model for each of the different model types in the single model approach. So in the single model approach, it turns out that plain backpropagation provides the best results, with plain backprop deep learning being the second best approach. where deep learning just means that the model has more than three uh, hidden layers. We find that backprop through time, LSTM, and GRU have considerably worse performances. Now we see a comparison of the best models in each model type in terms of the time in milliseconds. So the plain backpropagation and deep learning models prove to have the best performance in this category as well. Based on the last two slides, we can conclude that the best model is the plain backpropagation model. So the graph in this slide shows the predicted values versus the actual values for the plain backpropagation model. Finally, we ran a plain backpropagation model on our entire data set, and this resulted in an MSE of 0.00015449. After comparing the three approaches, we find that the static supervised learning approach using embeddings provides the best results. This might have something to do with the fact that the data is at a more granular level, which is the store family level. So that could be a contributing factor to its success. That concludes our presentation. Thank you.